in this part, I would like to look at 3 specific details of a soft sphere DEM simulation. And the first thing is the collision time analysis. We have seen that in the soft sphere method, depending on how we choose the stiffness of the particles, so this Y is the Young's modulus, which is in the classical linear spring dashboard proportional to the spring stiffness, is very important because it decides on the collision time. So if you have a hard or relatively hard particles, very high stiffness, the collision duration is very short, and on the right hand side you see a relatively soft collision where you have huge overlaps. The question is, how does this time scale of the collision scale with the stiffnesses, and how shall we choose the time step in the soft sphere method? If you think about solving Newton's equation of motion in the differential form as it is done in the soft sphere method, we must pick a time step, and the size of this time step, obviously this delta t, has to be smaller than this collisional timescale tc here. So it boils down to predict the collisional timescale tc, because then we know from numerical practice that we should choose the time step as, let's say, 10%, for example, as this collisional time. So the scaling of this stiffness is important. I told you before, K is the stiffness in the simple linear spring dashboard model. From dimensional analysis, you will see that this is proportional to the Young's modulus and a particle diameter. We will talk about the F here in the very soon, right? And also based on dimensional analysis and a relatively simple oscillation theory, you will see it later in greater detail, you will find that this collision time is proportional to the square root of the mass divided by the stiffness. And if you then replace the mass with particle volume and particle density, you will arrive at this equation here that tells you that this contact time is proportional to the square root of the density over the effective Young's modulus. Okay. There's another equation for the so-called Rayleigh time. This is also an important equation, but again it boils down to the important information is that this collisional time scale, and hence the time step, is proportional to the square root of the density divided by the Young's modulus. Okay. The prefactor here is related to the particle size, so Rp is the particle radius, here dp is the particle diameter, right? So you see, the smaller the particles, the smaller this time scale, the smaller the time step has to be. This is a very important thing. The second important piece of information that you find very often in the theory is the so-called effective collision parameters. Well, what are effective collision parameters? They are also called reduced or equivalent parameters, and the reason for introducing these parameters, effective parameters, is that we want to treat particle-particle collisions with the same equations as particle-wall collisions. That means we don't have to rewrite all the equations for particle-wall or particle-particle. We can just say, well, this is an effective collision as if a particle would collide with a wall. The effective parameters must be calculated for the Young's or shear modulus, for the radii, and of course for the diameters as well, and the masses. So here are the equations that have been derived for these effective properties, and here I and j are just the two indices of the colliding particles. You will always find I and j here indicating this is the first particle in the collision, this is the second particle in the collision. Good. For two identical particles, well, if I is j, you will find, and this is also important, that the effective Young's modulus, for example, is the Young's modulus of the particle's material divided by 2 multiplied by 1 minus nu I squared. So this is not the velocity, this is the Poisson ratio as you will find it in the nomenclature. For the radius, it's Ri over 2, so please be careful. The effective radius of a particle and the effective diameter of a particle is, for a particle-particle collision, the radius half or the diameter half. And for the mass, again the same. So please always be careful whether here is the effective mass or the true particle mass. The third part I would like to discuss with you is contact detection. Well, why is contact detection important at all? Well, you have seen in the soft sphere discrete element method, we need to calculate the contact forces between particles. Those contact forces depend on the overlap between two particles. And of course, this overlap is only relevant if particles are really in contact and overlapping. The problem now is that if we have n particles, for example 100 particles in such a box, we would have to perform n squared contact tests. And the reason for that is that we would have to loop over all the particles n, and within each of these loops over all the particles n, we have to then do again n checks. So n times n is n squared, and that leads to an excessive amount of contact tests that we cannot do. So the important and basic idea behind this is to not do these checks, but only consider the neighboring regions of a particle. For example, if we look at a specific particle here, then we know that this could only potentially contact particles in these neighboring regions. In 2D that would be 9, in 3D that would be 3 cubed, that would be 27 regions, right? So those close particles here are called neighbors, and these particles are managed as in so-called neighbor lists. Again, neighbor lists are nothing else as a list of neighboring particles for a specific particle. This is again to avoid identification of these neighboring particles, so it's a matter of computational efficiency. If we do all this, if we have this neighbor search grid and these neighbor lists, we end up by much more efficient simulations, and we only have to perform order 20, and 20 is simply the typical number of particles in the neighbor regions multiplied by the total number of particles in our simulated domain n. The next question is, how can we identify those close particles? And obviously it has to do with the bin size. The smaller this bin size, the less amount of particles we have as neighbors, and the neighbor list is shorter. How can we now define the smallest bin size? That's the critical question, right? And for that we need to apply a two-step approach. The first step is that we consider a so-called safety distance or skin distance, and we need to do this because this neighbor list build, this neighbor search algorithm is not done at every instant in time, but there is a certain time interval in between which we refresh this neighbor list, and in this time interval particles can move due to their velocity, for example, right? So this skin distance has to account for this movement of particles in between the neighbor list building. And the second step is that we consider how far the particles can move within this time interval between neighbor list creation. Again, this is the skin distance, right? These red particles, these are two particles of identical size. The size doesn't matter here too much, but just to illustrate it to you, this is the physical location of the particles at the time 0 where we have created the neighbor list, right? And this is the skin distance, right? So if you now consider a worst case scenario, and here again we have sketched this Eulerian search bin, right? In the worst case, the particle moves, this right particle moves left to the maximum distance, and the particle on the left moves right to the maximum possible distance, right? So if you think about this, then you will find that this minimum bin size is simply the sum of these two radii of the particle plus skin distance. So it's the sum of the radii, the physical radii of the particles, this distance and this distance, plus 2 times this skin distance. Again, you have to be careful as always, and in case of so-called non-contact interparticle forces, so forces that also exist when particles are in contact, and you will see that later that there is a quite large group of this group of forces, we have to enlarge the spin size for the distance essentially we can have these interparticle forces. So you have to be careful when picking these spin sizes. In summary, again, it's very important to not do these naive n-squared contact checks, but to introduce bins and skins to then end up with this order 20 times n contact checks. If you're interested in more details regarding contact detection, there is an excellent reference, Voskuil and Sarkar, that gives you more details about this.